and today he's going to talk about scalar fields in cosmology. So please give a big round of applause for Swagat.
Hi, sorry for the delay, and also I should apologize that my voice is a bit down because I got cold. So if I seem a little less excited, then assume that I am excited from inside. Okay? Alright, so I am going to talk about scalar fields in cosmology. Just wanted to know how many students are first year or second year or third year? Okay, very good. Fine. So I'll go accordingly. You will know specifically. So I'll go accordingly. So cosmology is the study of the whole universe. Just like in physics, you study systems. You have a system which is described by some mathematical structure, and then you study the time evolution of the system given some initial conditions. The same thing you do for cosmology. But the only difference is that first thing is you are applying all the laws to the whole universe. The second difference is that you have to find the initial conditions. You cannot say I will put this initial condition and see how universe becomes at late times. That you cannot do because we have just one universe. So you have to find out the initial conditions of the universe. So in that way, initial conditions are very important in cosmology, which is not important in other branches of physics, like terrestrial physics, like fundamental physics. It's not important. So I would say the theme of the talk today is initial conditions and fine-tuning. What we would like to know is that the universe that we see today, first thing is, we are all physicists, so you know this, but I just stress this, that the universe that we see today is not the universe that it has always been. It was different in the past, just like Earth. Earth was different, and there were no human beings 2 lakh years ago, and the continents are constantly drifting. So Earth doesn't look the same. Similarly, the universe doesn't look the same. You see stars and galaxies everywhere. That was not the case always, and that will not be the case always. Okay. The talk is a bit technical. The topic is a bit technical, but I will try to make it simple. And students or PhDs or postdocs who are more interested in going deeper, please ask a question and go deeper. Any point you want to go deeper, just ask. Okay. Fine. So just mention that I have been working on cosmology since a couple of years. So these are the kind of work that I have been doing. I just want to mention that I don't work on dark energy. I work on dark matter and inflation. So there are 2 projects that I have done. I will probably talk about the second project a little, but mostly about initial conditions in cosmology in relation to dark matter. Can I speak loudly? Is it audible? So we will talk about dark matter. Okay. And anyone who wants to discuss about inflation, please catch me tomorrow because I am going tomorrow. We can just talk about inflation. Inflation, I think, is a more important and more exciting topic. Okay. This is not necessary. So for first year, second year, or third year students who have not done special relativity, you know that generally in a geometry we define distance between 2 points, right? So if a point is given by x1, y1, another is x2, y2, then distance between them is x1 minus x2 square plus y1 minus y2 square. Right? This is plain Euclidean geometry. There can be some deviations from this kind of geometry if you have a different kind of set. Here your set is the space of all points x and y. If you take a set which is space of time and space, then distance between 2 points changes. Okay. So this is special relativity. We say that time and space should be seen in a sort of similar way. And if some event happened, any event happened, like a bomb going, right? And if one observer calls it time t1, x1, and y1, let's just think one dimension. Okay. Another observer says the same event as t2, x2. In normal Galilean relativity, you have studied that t1 equal to t2. For everybody, it happened at the same time, but space can be different. For me, if it is at x equal to 5, for him it will be some other x. Okay. This is not true in general. The thing that we think is just because of our evolutionary brain that we are used to slow moving objects. For slow moving objects, that's a good approach. If one observer is at rest, for example, with respect to you, and another is moving at a very high speed compared to speed of light, sort of nearly at the speed of light, then these times will also change. They will also see different time. Okay, that is special. Now so time is changing and space is changing, but there is one quantity which remains same, which is the distance between space-time points. Not between space points, but space-time points. And that distance is typically this is a kind of distance, right? Minus dt square plus dx. Okay? This quantity remains same for any observer. Okay? This is if one observer is moving at a constant speed related to the other observer. Now, if one observer is moving at a variable speed with respect to the relative observer, then that variation of speed can be thought of as gravity. So you can say there is gravity, Earth is pulling some object because of gravity, or the object is in some kind of a non-inertial frame where the speed is changing. Okay. In that case, this distance will be very different. This distance will be given by, in general, it will be given by like this. Where this mu means mu and mu run from 0, 1, 2, 3. Okay? And there is a summation over mu and mu. This is for the first years. I'm sorry if the seniors are getting bored. So if mu is 0, it means time. Okay? So x0 means time. x1 means x, x2 means y, x3 means z. Fine? So it's a generic function. And where this g mu in this case was -1 and 1. And for similar for y1, for z1. In general, it can be some function of x and time. Okay. So what gravity means in general theory of relativity, gravity means distance between 2 points, any 2 points in space and time is different at different places and is different at different times. If I take the same 2 points, it depends on where I am. If I am near Earth, the distance between 2 points is something else. If I am far away from Earth, the distance between 2 points is something else. This is Einstein's theory of relativity. So Einstein's theory of general relativity, which is the theory of gravity. Okay. So gravity is nothing but distance between 2 points, and that distance is given by where I am and what kind of object is there. Okay. So if you think that universe is made up of a lot of galaxies and they are all equally distant. Okay. All the galaxies in the universe are equally distant, like a Poisson distribution, like a random, equispaced and equally distant. In that case, such a universe will look homogeneous and isotropic. Everywhere it will look same, wherever you go. If the universe is infinitely big, I am for now assuming. Either it's infinitely big or it's finite but it's closed, like the surface of a sphere, which is also homogeneous and isotropic. Every point is same, right? You can call any point a north pole of a sphere surface, right? So on such kind of a surface, now surface of a sphere is a 2-dimensional surface. If you go to a 3-dimensional surface which is homogeneous and isotropic, then distance between any 2 points will be given by this formula which I wrote. Okay, that is the distance between 2 points. And if anyone wants to know how this we can derive. We don't need any physics, just from mathematics you can derive. You can ask me, you can derive. Okay. So distance between 2 points is given by this, where r, theta, phi are the coordinates. Okay. Now this distance is almost same as the distance that you study in spherical polar coordinates. Only difference is there is a time part added because this is space time. Okay. Second thing is there is a of t, and third thing is there is a k there. Everything else is same, right? dr square plus r theta. This you know, right? First year students also know this, right? Spherical polar coordinates distance. The same. Only thing is there are two terms. One is a of t and one is k. These two are different. Okay. This k has to do with curvature. So till now you have been thinking of Euclidean space, which is flat, but space can be curved like the surface of the sphere. There the sum of three angles of a triangle is not 180 but different. That's why there is a k there. If the k is 0, then it's a flat space. If k is 1, it's a positively curved space like a sphere. If k is negative, then you cannot visualize it because there are no two-dimensional constant negative surface. But you can think for some time, you can think of a surface of a quadratic cube. Okay. For all our discussions here, we will discuss for k equal to 0 because observationally our universe is flat. Okay, there is no curvature, our universe is flat. So if you take any 3 points in space and shine laser light from one point to another, then from there to there, and measure the angles, it will be very close to 180 degrees. Okay? And this a of t is scale factor, which is a function of time. That means with time, distance between 2 points is changing. That's what you are seeing. Okay? And this is for a universe in which everything is distributed exactly randomly and uniform. Anything which is extremely random is uniform because all the points are equally covered. Okay? Otherwise somewhere it will be clumsy and somewhere it will not. Now this assumption is not exactly correct, we will come to it later. But for now we will assume that galaxies are randomly distributed. So universe is homogeneous and isotropic, looks same everywhere. And the distance between any two space-time points is given by this one. Okay? Now Einstein's theory, what it does, it tells you how this a of t changes with time. Fine. So how this a of t will change with time will be given by Einstein's equation. And that depends on what kind of matter is there in the universe. So Einstein's equation of gravity is the following. This quantity is a second order differential equation for this g mu, or for, in this case you can think it's the second order differential equation for a of t. Okay? And this side is just energy density and pressure. Okay? So it depends on what is the energy density at any point and what is the pressure at any point, that a of t will be determined by that. So energy density and pressure can be different. For example, if you take a pressureless substance like a dust, if there is dust are not colliding, so there is no pressure. For them, the evolution of a of t will be different. If you take something which has pressure, like if you take black body radiation, do people know about black body radiation? There, the pressure is related to energy density by 1/3 factor. Okay, so such a substance has pressure. Such kind of substance will behave differently. So the distance between 2 points will change, but it will change differently depending on what you put in the universe. If I only put light in the universe, then the distance between 2 points will change in a particular way. If I put only dust in the universe, it will change in a different way. If I put a lot of things, then it will change everything. Okay? That is a very simplified version of this. So Einstein's equation predict how these quantities change. So we have only one important quantity here. I have put k equal to 0 for you. Only important quantity is distance between 2 points, and that is changing. I am stressing it again and again because this is not what we are used to. Like if I say distance between these 2 points, if I come tomorrow, it should be same, right? If I come after 10 years, it should be same. And the distance between 2 points here, if I measure, and here if I measure, the same 2 points, then it should be same, right? That's not the case because of gravity. Because of gravity, that changes. Okay? And these are the equations. You have to solve these equations. Only thing is, you have to know a relation between pressure and density. Just like for black body radiation, pressure is 1/3 of density. Similarly, for any generic matter, pressure and density will be related by some complicated formula. Only thing is, in the universe which is expanding, we can think that no particles are going and colliding with them. This is another approach. So galaxies are just there, they are not colliding. This is also not exactly correct, but this is correct in early universe. I will come to it. But now we will assume galaxies are not colliding and interacting. They are just changing. Their distance is just changing. For such kind of a system, pressure can be related to density by this kind of formula. Pressure equal to some number times density. And that number is 0 for dust or for galaxies. Galaxies are not colliding, there is no pressure, right? Galaxies are just there. Okay? And that is 1/3 for black body radiation. And that is, that can be something else. That can be 1, that can be -1. That can be anything. So that is a crucial. There are only few equations that we will deal today. If we can master those 3 equations, then we can understand the full theme of the talk. Okay. First equation is how A changes with time.
What is stiff matter?
What is stiff matter? A stiff matter is such that pressure and density are exactly same. W equals to 1.
That's the definition.
It's a stiff matter. Okay.
What are the examples?
There are no examples. You don't find it on Earth, but quantum field theoretically you can find it. The matter that are on Earth, they are not stiff. There is no stiff. Also, there is no matter on Earth which has negative pressure. Have you seen a matter which has? You have seen. You have never seen a matter with. Have you seen a matter with negative pressure? What is the definition of pressure? Okay. Force per area is a bad definition of pressure because force is not a good object in relativity. So the definition of pressure is work done per unit change of volume. Okay. You change the volume of a system and see how much work it does. If it gains energy by increasing volume, then it has negative pressure. If it loses energy by increasing volume, then it has positive pressure. Like a normal gas, it expands, it cools, so it loses energy by expanding. So those are positive pressure. Negative pressure is a rubber sheet. You take a rubber sheet and you just expand it. Then it has more energy now, right? Compared to when it was not stretched. So you increase the volume, but you gave energy to the system. Such kind of system has negative pressure. Okay. Such kind of things exist in sky, and those are properties of space and time. They are called vacuum waves. That topic will keep to dark energy and inflation if someone wants to discuss. Today is dark. I am just familiarizing you with the equations. We can take as much time as possible for familiarizing, because once you are familiarized with this, we will go ahead first. Once I finish it, I will again say what all are necessary. Okay. So we just solve these equations. If you solve these equations, see how many unknowns are there. There is A depends on rho, and rho and P are related by this formula. Right? So if you solve this equation, rho dot equation, here there is only 2 variables. Rho dot, which is rho as a function of T, and P and rho are same. So just one variable. Then find rho as a function of time. You take it and put it up in the second equation or in the first equation. You can solve for A as a function of time. Okay. This H which I am calling is A dot by. In a introduction to cosmology talk, I would start very differently. I would tell what is cosmology, where galaxies are expanding, what is the meaning of Hubble constant. But I have given that talk here, I don't know how many times, at least 10 times. I don't want to repeat it. But you can ask me, it's fine. So you solve this equation and see how rho depends on A. And this is the kind of dependence you get. So rho depends on A like this. So if A is increasing, that means if distance between 2 points is increasing, then the density is decreasing in the following. Okay? This is a dependence. So for matter or dust, that W is 0. There is no pressure. Pressure equal to W times density. If W is 0, there is no pressure. Okay? By pressure you mean something is colliding. Right? To have pressure, you know kinetic theory of gases. Same logic. A system has a pressure, means they should collide very fast. They are not colliding, the system doesn't have pressure. So that is how the distance is changing with time. Now this says that distance between 2 points is changing in time. It can increase with time. For example, you say T to the power some number, which means universe can expand. Okay. So you take 2 galaxies and keep them somewhere, and and with time the distance between them is increasing. Any two galaxies, anywhere, it's increasing. That means universe is expanding. This is what was observed by Hubble in 1929. Okay. When he observed that universe is expanding, he probably thought that galaxies are going away from each other. It's like all the galaxies were nearby, and somebody blasted some kind of a bomb, and then the galaxies started going away from each other. That's what he thought, but that's not the case. That we know that universe can expand because of gravity. In Einstein's gravity, not Newton's gravity. In Einstein's gravity, distance between 2 points will change depending on what matter. Okay. And if you put galaxies randomly, then distance will increase or decrease depending on initial force. Okay. So this is expanding universe. Fine. Now there are 4 important epochs in the universe. How much do people know about cosmology? Like, what all do you know about cosmology? Do you know that what is Big Bang? Like just popularly, what is Big Bang? No? What is Big Bang? I just want to see so that I will know what to say. Can anybody tell me what is Big Bang? I should have given a talk introduction to cosmology, not scalar physics. Anyway, but you will learn something today.
It's like the event of creation.
Sorry?
The event of creation.
The event of
the
creation
point after
of what?
which we have matter and energy in the universe.
Well, okay. So that is a popularly known definition of Big Bang, which is not correct. When a physics person working on Big Bang or universe says Big Bang, what he means is that now it's not a hypothesis, it's a tested theory. So theory of universe in which universe was hotter and denser at early time. Okay? As you go to earlier and earlier, it was hotter and denser. It can get as hot as possible. It can get 10 to the power 24 degrees Celsius. So electrons will fly apart from nucleus. Nucleus will fly apart. Okay. Such kind of, from there, universe was expanding and cooling, and today you see all the galaxies and stars. That's a great story. How actually cosmology means to study how universe began there and then expanded and become what it is today, and what it will become later. What is the geometry of universe? What are there in the universe? These things are what are there in the universe. Okay. There is light in the universe. There is a lot of light in the universe. The density of that light today is very less, but in early universe the density of light was very high. Why? Because you saw the density, how density changes with A for different W. Okay. So for light, W is 1/3. So density falls as A to the power -4. Okay. So density falls very fast. So if today it is low, if you go back in time, it should rise fast back. So at some point of time, it was mostly light and less matter. And today there is more matter. So today there is more dark energy. So this is not my today's talk. So I am not talking about it. Fine. So what is a scalar field? So so the way we describe nature today is not by Newton's law, or not exactly by non-relativistic Schrodinger equation, which you would have seen in chemistry. We describe nature by saying that everything that you see in the nature are formed by fields. Okay. There's a fields. Fields means they are functions of space and time. There are different kinds of fields. Each field has an associated particle. Electron has an electron field. Light has light field, electromagnetic, which you know, electric field and magnetic field. Okay. Similarly, each field has a particle. Similarly, you know Higgs particle, you must have heard about that. Higgs particle. So Higgs particle is part of a field which is a scalar. What I am saying today is there can be other scalar fields in the universe, not just Higgs. Okay. If such fields are there, then there will be such corresponding particles will be there. If such particles are there, what are they doing in the universe? Okay. So what I will claim today that some of those fields can be acting like dark matter in the universe. Now my talk is on dark matter, so I assume you know about dark matter. So how, like popularly, have you all heard about dark matter? First year junior students, have you heard about dark matter? What is it? Anybody can answer. It's an informal talk, so we can just interact with it. Can somebody
It doesn't interact normally with electromagnetic waves.
I thought somebody would say something which is dark. Dark matter is not dark, it's a wrong name. Dark matter is invisible. It is invisible by all means. The air in this room is invisible, but that is invisible in visible light. If you change the frequency of light, then this air will finally interact, and so this room might look opaque in some other frequency of light. But in visible light, it is invisible. It doesn't interact much with this atom. So they are there. Dark matter is completely invisible to light, any kind of light, because it doesn't interact with light. Okay, it interacts through gravity. Now, because and we know gravity is a weak force compared to electromagnet. So because universe, all planets, all stars are neutral from outside. They are all neutral. So the only force which acts in the universe is gravity on large scales. Electromagnets, there is no charge, overall charge on a star. So one star doesn't attract another star by electromagnets. Same is for galaxies, same is for planets. Only force is strong force. Gravitational force, which is very weak. Fine. So this dark matter can attract each other, or they can attract other matter through gravity. In Einstein's theory, any object attracts any other object if it has energy density or pressure, which is a bit different from Newton's theory. Newton's theory, any two objects attract each other if they have mass. Right? In Einstein's theory, if you have mass, you may not have mass. If you have energy or if you have pressure, you attract each other. Okay. So in Einstein's theory, if you take a star which has pressure, and if you take another object of same size, same mass, same density but doesn't have pressure, then they have different gravity. Okay. So the scalar fields, they are there in universe. They are there in the universe, and what I am claiming is they can act like dark matter by the following way. The density of a scalar field is given by a kinetic term and a potential term. Just like you have seen a particle which is moving can have a potential energy and a kinetic energy. Similar. And the pressure can be given by kinetic term minus potential term. Okay? So that W which I was talking, which is pressure by density, will be given by that formula. So whatever W you want can be given by the scalar field by adjusting what is the kinetic term and what is the potential term. Remember what is W? Pressure is related to energy density by W. In the expanding universe, if universe is expanding, then pressure is related to the density by this W. And this W can be, for a scalar field, this W can be anything. Think if kinetic term is 0, what is W? If the kinetic term is 0, if a scalar field is not moving, minus 1. Okay, this negative pressure substance. You said you wanted negative pressure substance, rubber. You can have. If potential energy is 0, potential term is 0, then what is W? Plus 1. This is called stiff band. And then you can have any other W. But W will always lie in between plus 1 to minus 1. Okay. So this is why scalar field is important. Every substance that exists in the universe is characterized by this equation, which is called an equation of state. That's the name. Equation of state, where W decides what is the equation of state. If W is 0, it's a pressureless substance. So it's called matter or dark matter. Okay. If W is 1/3, it is light. So a scalar field can act like light. Only difference is the scalar field is a scalar particle, and the light is a vector particle. So there will be spin differences. There won't be polarized. But as far as expansion of universe is concerned, a scalar field can act like light. Okay. What lights are doing is scalar field. So it can do anything that you want. Okay. And something is called dark energy, which is not today's talk. Something is called dark energy if its W is less than minus 1/3. Can you get less than minus 1/3 from here? You can get. Right, make this bigger than this. So whole thing becomes less than minus 1/3. So you get dark energy. So the scalar field you can get anything. Okay. What we will focus on is dark matter. So we have a scalar field and a potential field. Okay, before I go ahead, from now on the topic will become easier for people who are new for that. So I will just what I have told. Okay. What I have told is that gravity means distance between any two points in space-time can be anything. Okay. It depends on what kind of matter you put. If you put in the universe, if you put matter in a homogeneous isotropic, like a uniform matter everywhere, then the distance between any two space-time points will be given by this formula. Okay? This is not from Einstein's equation. This is just from symmetry. You can calculate this. It takes some time, but we can calculate this. Why it looks like this? Just a homogeneous isotropic space-time will have the distance formula this. Now Einstein's equation will tell us what is that A of t, how it changes with time. Okay? So first thing we learned that distance between two points can be different everywhere, and it can be different with time also. So if it is increasing with time, we say universe is expanding. If it is decreasing, universe is contracting. You observation will find universe is expanding. So we have already a model which models expanding space-time. Okay? Second thing is that how A of t will behave depends on what kind of matter you put. And what kind of matter you put is characterized by pressure and density. And in an expanding universe, pressure and densities are related by that formula. Okay? So depending on what is the W, you will know how it is expanding. That thing is clear, right? Now, dark matter is something which doesn't, which are not colliding with each other. There is no pressure. So for dark matter, W equal to 0. I want to model dark matter by scalar fields. Why I want to do it? I want to do it because there are many fundamental theories of physics which predict a lot of scalar fields. They say that there are scalar fields in the universe. A lot of scalar fields. Where are they? We don't see them. We see electrons, we see protons, we see neutrons, we see light. But we don't see those scalar fields. Where are they? We have seen Higgs. But we don't see those other scalar fields.
This scalar field that you are talking about, so gravity does not care about the speed of that particle?
Sorry?
The gravity does not care about the speed of that particle? Spin, because suppose some substance somewhere is one time.
Exactly.
So that normally, suppose you consider radiation, that should be spin one.
Good question.
But
It
here
doesn't. It doesn't. It does just.
some kind of effective kind of.
Sorry? Yeah. So what gravity cares about is spin, which is the energy momentum tensor. Okay. And for a uniform homogeneous and isotropic space-time, energy momentum tensor is just density. It's just a matrix, which diagonal matrix, which has energy density and pressure. That's all. So gravity only depends on pressure and energy. As far as that is same, a spin zero substance can behave like a spin one substance. Only gravity is same. But in our universe, when universe was early, it was dense. Light and electrons were interacting. Right? So in early universe, it will matter actually what you. Only gravitationally doesn't matter. Yes. The spin is not coming to picture as long as T mu is. That's Einstein's equation. So I am proposing that such scalar fields which we get from fundamental theories can act like dark matter in the universe. Other than those scalar fields, there are other things which can act like dark matter. Those are called WIMPs, weakly interacting massive particles. Okay. Those particles can act like dark matter, and they have a very interesting criteria. That if they are weakly interacting, there are such particles in the universe, they are there, and they are weakly interacting. Weakly doesn't mean English word weak. Weakly means weak interaction, weak nuclear interaction. There are 4 kinds of interaction: gravity, electromagnetism, strong interaction, and weak interaction. Weak interaction is responsible for your decay process. Okay. Now, if such particles are there weakly interacting, then today their density fraction should be 1/3, which is what we observe. Today we observe that our universe is made up of 70% of dark energy and almost 27% of dark matter and 3-4% of normal matter that we are made of. So all the electrons, protons, galaxies, stars that you see today, all the planets, they only form 3 to 4% of the total energy density in the universe. The rest of 96% is unknown. Out of them, 70% is a very weird quantity, which has negative pressure. We call it dark energy. That I am not talking today. 30% is a quantity which is just like galaxies, but they don't interact with, they are just like electrons and protons, but they don't interact with light. This is what this WIM hypothesis is. If that is true, then they should always be 1/3 today. And that's what you see. So that's a very exciting theory. The only problem is that we have never found them directly in lab, while we should have. So there are experiments which should directly detect. They will interact. So you can find some detector and wait. They are passing through Earth. They are everywhere in the universe. So they are passing through Earth all the time. So they should bump into your detector sometime. And we have actually created very sensitive detectors, but we have not found them. So now we are moving to some alternative explanation of dark matter. By the way, there is another explanation, which is that there is dark matter because of there is no dark matter. It's just that law of gravity is different. So Abhishek told me that he gave a talk in Science Day where he talked about rotation curves and how dark matter was detected. So I didn't talk about those things. Some talk. So I assumed people know, so I didn't explain those things. So what happened is the detection of dark matter was done through gravity. There was a system which was behaving differently from Newton's law. So they thought that there are two possibilities. Either Newton's law is wrong, or there is something new you cannot see. I'll give you an example. First example is, you know that Neptune was discovered because of weird motion of Uranus. You know this story? That astronomers looked at Uranus is moving very weirdly, and then some theoretical astronomers just calculated that if there is a planet there, this big and at this distance, then Uranus should behave this. So dark matter is this kind of hypothesis, that your law is same. Your law is Newton's law, but the behavior is weird because there is something extra. Okay. While other example can be that Mercury was behaving very weirdly when it's moving around the sun. It is not moving in perfect ellipses. It sort of precedes. Okay, the ellipse sort of shifts around sun. So people thought again probably there is something extra which is pulling it, but no extra was found. So finally Einstein replaced Newton's law by Einstein's law, which would explain it. So when you see something weird, either law is wrong or something extra is there. Now in physics, the way we work is called first to be conservative as much as possible. So we don't keep on changing our laws. We just don't say, it's not working, the law is wrong. That we don't do. We just push it as much as possible. We say, okay, maybe there is something extra, something extra. If nothing works, then we change our law. Fine? So now we are approaching dark matter in that way. But there is a second reason. There is indirect evidence of dark matter which is extremely strong, which says that there has to be dark matter. It's not law of switching, which I can discuss if you want later. Okay? So what I am saying is that in the universe, the evidence of dark matter is very, very strong. If you ask me as a personally, if I have to bet, I would say 99.99% that there is dark matter. And I can be wrong, so I leave those 0.01%. So now we are saying these extrastellar fields can act like dark matter. So they can act like dark matter is W is 0. First. Second thing is, if they don't interact with electrons or light in electromagnetic wave. Okay? So they don't interact with light, and if that W is 0. That's what I am trying to achieve from a scalar field. Okay? I can achieve that if I have a potential. This is my V of phi. This is my scalar field and this is a potential. Okay? So if I leave the scalar field here, what will happen? The scalar field will roll down, right? Just like it will roll down and will start oscillating. Fine. I will first prove that if a scalar field is oscillating and it is oscillating faster than expansion of the universe. Universe is expanding and scalar field is oscillating. If the oscillation frequency is faster than the expansion of the universe, rate of expansion of the universe, then this scalar field will act like a dark matter. Okay. Before that, we have to know how the equation of scalar field is given by. You know, if potential is V, force is V dash, right? Derivative of potential. So typical equation should be, you know, the simple harmonic equation. This you know, right? Everybody knows this. For simple harmonic potential, V of phi is just half m square phi square, right? But half kx square, like you say. Okay? Only thing is in an expanding universe there is a friction term. You see this is a friction term. Have you done damped harmonic oscillation in Klepner-Kolin or some other where? You have done this, right? So this is like a friction term. Only difference is in an expanding universe this friction term is not constant. This term is changing with time. So you have a damped harmonic oscillator. A scalar field is like a damped harmonic oscillator in the universe. And the friction term is a time dependent term. So it has a friction of coefficient which is changing with time. That is how the scalar field is going to behave. So it is not going to slide down freely. It is not going to slide down freely. There is friction, so it will slide down very slowly. What if you give it a very high initial velocity? Then it can slide a little faster. But friction term is also proportional to velocity. Look, there is phi dot here. So more the velocity you give, there is more friction. So it will again bring it to rest very soon. Okay. So the natural motion of a scalar field in an expanding universe is to move very slowly. Fine? So if you leave it somewhere, it will move very slowly and later it will start oscillating. Now if the oscillation frequency is greater than expansion of the universe, in that case, if you take V of phi as some phi to the power 2p, if you take V of phi as phi to the power 2p, like phi square is simple harmonic. You can say phi 4, phi 6. In physics, in quantum field theory, this kind of fields arise. So I have written it generalized. Then W can be given over average over oscillation. W can be given by P minus 1 by P plus 1. Okay. So if you take P equal to 1, which is phi square, W average is 0. So over one oscillation, the scalar field is behaving like dark matter. Fine. So this is the model of dark matter. And this was the first brilliant idea of dark matter in 1979 by Becky Quinn and by Frank Wilczek and Weinberg. All those people. This was the first model, and these models were in the context of something else. They are called axions, and those are particles which which are necessary to explain some problems in strong interactions. Just assume that fundamental physics.
The oscillations are in something in the phi space.
Sorry?
The oscillations is in the phi space. Right?
Yes.
So
Yeah.
So could you explain why is it that?
Why is it?
Why is it that when you need the V phi, so the oscillation is in kind of phi space, it's not position.
No. There is no position here. The equations look like, so phi is not position. Phi is the value of a field. So value of a field is changing with time. Think of electric fields almost. If you go to any space, this is same at any space. So you stand here, you ask what is electric field doing. We know what electric field does if the light is passing. It behaves like simple harmonical. So wave, right? It behaves simple harmonical. Then it shifts to next point, it behaves simple harmonical. Similarly, this scalar field is behaving the same way everywhere in space.
I'm saying that this phi would be at a given
at any x.
at
At any x.
but it is fixed for a given graph. As you are
For a given?
for a given so this graph would be at a given fixed space-time point.
No, everywhere. Everywhere the scalar field has same value and has same potential. So it's behaving equal. Now why everywhere it should be same? That's because universe is homogeneous naturally. So it cannot behave differently at different points. Then the homogeneity is broken. Second thing is cannot behave differently in different directions. Isotropy is broken. Okay. So at every point in space, this scalar field is at some value. And how it will change with time is governed by the equation which I showed you. It's a friction term. It's like a equation with a friction term and the friction coefficient is changing. The coefficient of friction is actually Hubble constant, which is the expansion rate of the universe. Okay? If universe expands, then there is.
Why for simple harmonic potential the expectation of omega phi is zero?
I have given the proof here. It's a derivation. You can go through it. This is a derivation. So, roughly physical speaking, what happens is, if it is simple harmonic, then over one period of oscillation, the value of kinetic term and the value of potential term are same. You know this.
Yeah.
Very well you know. Right? So, average value remains same. Because it remains in the cancel out. So, if you remember the expression for W, you see kinetic term minus potential term is there. If that average is 0, then W is 0. That's what is happening. If you take some other potential, that is not going to happen. Okay. Sometimes it will be more potential dominated, so you get dark energy. Sometimes it's more kinetic dominated, so you get fastly moving dark matter. Okay. So a scalar field oscillating around the minima is behaving like that. So if I claim that today all the dark matter is there, because at every point in the universe there is scalar field which is oscillating. I am done. It's a good model. So there are two things. What next you should do is, we have assumed universe is homogeneous and isotropic, which is not true. Which is not true because we see a galaxy here, a galaxy there, in between there is nothing. Right? So universe is actually clump. So it is homogeneous and isotropic.
When you speak about homogeneous, you speak about some particular distance at a scale, right? The 200 megaparsec.
Actually, those are some. You are not wrong. Those are not actually correct. But I'll tell what you are saying. What he's saying is, if you look at this surface. See, this is a very informal lecture. I have no aim to finish something, so I can go as slow as possible. My aim is just to talk. So suppose the surface of this table. Okay. If you look from outside, from here, this table looks very smooth, right? It looks same. Every point looks same. But if you take a microscope and zoom in, you will see different atoms are at different places. But that analogy is a bit different for our universe. That's simply because here the atoms are arranged in some particular way. It's a solid. Solid atoms are regularly arranged. In universe, galaxies are not that way. They are very clumpy. Somewhere they are clumped and somewhere there is void. That is how it is. But early universe was not like that. Early universe was extremely homogeneous nature. It was like a hot soup of electrons, light, and nucleus.
So at every scale, from
early universe
micrometers to nanometers to computer, at every scale was homogeneous.
Up to nuclear scale.
Up to femtometers.
Up to nuclear, from nuclear scale to any high scale, it will look completely homogeneous, like a soup.
So above the Planck's length, above that it was complete.
Not Planck level, nuclear. But today, if you want to see universe homogeneous, you have to go to big scales. Like megaparsec scales, 100 megaparsec. I realized the problem is because I thought it's you people come to astronomy club, so you know these things like megaparsec, dark matter, rotation curves. So I assume. I'm sorry, if I knew this, I would have prepared the talk for just introduction to cosmology rather than scalar fields. Okay, but anyway, we go. If you want to ask me, ask something. I have no aim to finish some particular parts. Fine, should I go ahead? Okay. The problem is, first thing is to form structure in the universe. Let me tell you the best way we can think of dark matter physically is not those rotation curves. You know what is rotation curve? What I am talking about. Tell me if you don't know, I'll tell you. I don't mind. You don't know, right? Okay. So you know that there is sun in the center and the planets are rotating around sun. As you go away from center, you see planets are rotating slow and slow. Right? That's because gravitational force falls as 1 by r square. Force falls as 1 by r square. Right? So they move slow and slow and slow. But if you do the same for stars around the galaxy, stars are moving around galaxies. If you do the same, you will see that for almost all the galaxies, as you go from the center of the galaxies towards out and out and out, initially the velocity increases and then the velocity remains constant. It doesn't fall for a long distance. So this can happen if Newton's law is wrong, or there is something extra which is pulling the stars so that they can move and you are not able to see them. So our best approach is to be first conservative and then radical. Won't be radical from the beginning. So we first thought, okay, maybe Newton's law are still valid or Einstein's equations are still valid. That there is something extra. It's the historical introduction. The best way to think dark matter is not that. Is that dark matter is the skeleton of our universe. When our universe was hot, like a hot soup, okay, at that time, no structure could form. Because if you try to push a region to form a structure, you have to push, right? A structure should push and form something. Otherwise, they will all be homogeneous and isotropic. Like water. Do you see structures inside water? No. Everywhere density is same. But you see structure inside a bread. When a bread is being baked, you see somewhere there is bread and somewhere there is just gaps. Wherever there is bread, there is structure. And wherever there is gap, those are voids. Our universe is just like that on large scale. If if that is true, in the early universe there is a hot soup. If you try to form any structure, in the hot soup electrons are freely moving, so they are charged, and there is light. So light interacts with electrons, so there is a pressure. So if you try to push it, if you try to compress it, light will push it out. So it will just oscillate. So no structure will grow. It will only grow once universe becomes electrically neutral. Then there is no light and electron pushing going on. Because I told you light doesn't interact with normal neutral atoms. I can see you because light from you comes to me directly, even though there is air. That's the reason that light can flow. So if only after the universe became neutral, first structure started forming, then till today galaxies will not form. There is not enough time. Unless there is a skeleton already made, dark matter. Dark matter is there which doesn't interact with light. So from the beginning of the universe, once there is a structure compressed, dark matter will keep compressing, while normal matter is oscillating because of light pressure. And once universe becomes neutral, by that time dark matter has already formed some structure, like a skeleton. Now the normal matter will fall towards it. That's how the structure has formed. All the galaxies have formed that. All the galaxies clusters have formed this. That first galaxies formed the structure, and then normal matter fell into it after it became neutral. Okay, that's the best way to see it. If you don't have dark matter, structures cannot form. So this is the strongest evidence for that. But it's a indirect. Fine. So first thing is we have to care about how to form structure, which is not a problem. I'll come to it at the end because it's a bit difficult for first year people. So, what is the second thing is, in order to get, I told you there is 30% dark matter today, right? So in order to get 30% dark matter today, at some early time, you have to take the field and place it at a particular phi. If this is V of phi, at some early time, you take the field and have to put at a particular phi. Then they will slowly roll because of friction. They will slowly roll, and then later they will oscillate and give you the amount of dark matter that you see today. If you place it higher, you will get a lot of dark matter, and universe will start accelerating. If you take it, put it lower, you will get less dark matter and galaxies cannot form. And this is happening as per his question. This is happening at every point in the space. So some god has to take the field at every point in space and put at a precise value so that dark matter density today is that. If the value is higher, then there will be problem. Universe will accelerate, so before galaxies could form, they will tear apart. Okay. If it is less, then there is less skeleton, so the galaxies won't have time to form and we won't exist. So you understand? So it's like somebody cares about us and takes this field and puts it exactly as those values everywhere in space for you to exist in this model. This kind of thing in physics is called fine tuning. Okay. Some parameter value, some energy density has to be finely tuned in some early time so that today universe can exist. What I will argue is that if scalar fields are present, then such fine tuning is not necessary. Our universe is extremely generic. You can start from any point, you can put the scalar field anywhere, and it will give you today's dark matter, depending on what is your potential. This potential is m square phi square, right? It's just simple harmonic potential, like half kx square. For this potential, there is fine tuning. Okay. I'll show you the fine tuning. See this point A. You see the point A? What I plotted is the initial density of this scalar field as a function of this A. You remember A? Distance between 2 points. Actually, it's not the distance, it's the factor which is in front of the distance. We call it scale factor. It's just a name. So, today I have said today's value of scale factor to be 1. So, its log is 0. It's log scale. Okay. And in early universe was smaller. So, A was smaller. So, its log was negative. Understand, right? So, at some early universe, if my dark matter density is A, exactly A, then only I will get 27% dark matter. Okay? If the value is more than B, universe will start to accelerate and we will get structures cannot form because structures are trying to form if universe accelerates and take away all the structures. So galaxy cannot form. Okay? And if it is less than A, you get insufficient dark matter, so you won't get galaxies properly formed. There is not enough time. You have to wait till future to get galaxies formed. So this is extreme finitude. You see that value A, just 1 point. Okay? Depending on what we know about today's dark matter. If today it is 27%, then that is the A. If today it is 30, then some other A. But it has to be 1 A. Okay, so this is the problem. It's extreme finitude. I'm again saying, look, somebody, so this initial density, which you see, is given by initial field value. So somebody has taken the field value and put it there so that you see the universe to do. It seems like that. Or it was an accident. Accidentally, once universe began, accidentally the field value was there at some early time, so that you get today's universe. If it was different accidentally, it could have been a different universe. So either there is fine-tune, either it's an accident or somebody cares about it. Or the potential is not m square phi square, but a different potential. Then, this is the kind of potential I am talking, just to make it easy. If the potential is not m square phi square, but that kind of potential, I have written up, star density potential. Okay? If that is the kind of potential, and you place the scalar field somewhere up there, it will later come and oscillate. Okay, so I have written W average is 0 there. Look, oscillatory is 0. W average is 0, then it acts like a dark matter. If in this kind of potential you put, it doesn't matter where you put, a range of initial field values or initial density values will converge to one curve.
The finitude problem which you are saying that the initial amount of phi which you are having, initial phi. So because matter will also, because as AT would evolve with time, that would affect the dynamics of the matter also.
Of which matter? This scalar field matter or
Scalar field or other fields whichever is there. So that way, even if we don't arrive at the observed value of dark matter correctly, that would not mean that the universe won't exist. It may not be.
No, I'm not saying exist. It won't be the same that you see today.
Yeah, it won't be the
So
same.
you won't exist, because for you to exist, so how Earth is created? Earth is created because there was another star, right? That star stayed away its nebula and they formed all the higher elements, then Earth was formed. So for Earth to exist, there should be an earlier star. For that star to exist, there should be structure. So there should be some clumpy of galaxies. Now if you have less dark matter, galaxies won't be enoughly clumped. If you have more dark matter, before they clump, they turn.
But this kind of behavior of having the final result to be dependent on the initial condition is common for. This is the property of differential equations. That once you have this differential,
Yes, correct.
That is fixed. Like there is
That's
no
correct. That is exactly correct. But what is bothering here is the initial field value. So every differential equation is a differential equation in some other quantities. And what I am saying is, for most cases, those quantities where you put is not a big deal. For example, why Earth is at a particular distance from Sun? Okay. It has some initial velocity and a position. That's why it is at there. Right? It could have been somewhere else. That is not what I am saying. If it could have been somewhere else, then no problem. There won't be life, for example. But only those things which are there will be life. This is our universe just once. It just happens once. So either it's an accident, that I said. I am not saying either it's fine-tuned or it is an accident. It's accident, then no problem. Right? It's just an accident. In some other, if the universe was born again and the field value was different, then universe couldn't be. That's fine. I'm not denying. I can say yes if universe is an accident. What I'm saying is, it's possible to think universe as not an accident or not fine-tuned. What your point was, I'll just make it clear. He's saying that it doesn't have to be just fine-tuned. It can be just an accident. And because that was the initial value, this is what you see. That's what you're saying, right? Could have been. But do we want to think the universe is an accident? Right? I have no philosophical bias. What I'm saying is that it is possible to have a universe which is generic. Same universe, but generic. That's all I'm saying. I'm not claiming what is reality. I don't know. Okay. This red line is the dark matter curve. Okay, which I have done 27%. You see, from P1 to P3, wherever you start, all those red lines, dotted red lines meet on this red line. You see that, right? So this P1 to P2 is how many orders? 10. This is log scale, so 10 to the power 10. So 10 to the power 10 density come to one place. But this is because I am starting at an absolute density. No matter what is the density in itself, if it is within 10 to the power 82, then all of them will give rise to today's dark matter density. And so the universe, which looks to be clumpy and galaxies and clusters, planets and life, is a generic prediction rather than just an accident, or rather than somebody cares. So is this clear? Right, so this can happen, but I am not claiming that whether this is true. I don't know which one is true. But we have tests. You can test observation and say whether this model is true or their fine-tuned model is true. Okay, so we can observationally say true. I will come to it. These are details. I just mentioned that I said that dark matter should also cluster, right? We just talked about homogeneous and isotropic universe, but our aim is dark matter should cluster to form galaxy structure. So there is a length scale below which dark matter will not cluster. That's called Jeans length. Above Jeans length, dark matter will cluster. Below Jeans length, there is no structure. Okay? And that Jeans length is dependent on the mass of the dark matter. What I have shown is all those fine-tuned model and this model which I talked, I call them attractor model. All of them have same clustering property at date times. Okay, all the three curves meet. So that there is no difference between these models as far as galaxy clustering is concerned. Where the difference is the following. First difference is, okay, the first difference is between these kind of scalar field models and normal WIMP dark matter. Normal WIMP dark matter has a cuspy profile. Cuspy means as you go from the edge of a galaxy towards the center, the dark matter density should rise like this, sharp, like a cusp. Okay? While observational we see it's not a cusp, it's a smooth profile, like a cone. This is what normal dark matter theories predict. Is the density as a function of R. Okay? It doesn't go to infinite, it goes to infinite, but it's cuspy. But what you see observationally, the dark matter density goes towards center, is actually like this. Okay, so this prediction is a prediction of the scalar field model. First thing. Second thing is that below that Jeans length there is no structure. So if the Jeans length, the typical Jeans length of the scalar fields are around 1 kiloparsec. So you should not see galaxies below 1 kiloparsec. But normal WIMP dark matter predict that there should be galaxies structures below 1 kiloparsec, which we don't see observation. So you see why this model is motivated. This explains this kind of things. Now the difference is between those models in which it's fine-tuned and this model which I said attractive model. That difference is the following. Only this is the last line. This is behaving like a constant density before oscillating and then it behaves like dark matter. So I told you it behaves like dark matter when it oscillates. Like over one oscillation, the average is 0. So it's like a dark matter. Before oscillation, it's behaving like a constant density, while those red curves are not behaving like constant density. So if you can probe early universe, you can see the differences. And if you see the differences, you can say which model is correct. Then you can say whether universe is fine-tuned or accident, or it's a general. It's an observational issue, not a philosophical issue. Okay. And then there is a last difference that such oscillating dark matter models can be detected using pulsar timing arrays. There's some pulsar right there. And they can also be detected using gravity waves. Okay. Because the scalar field is oscillating, the gravitational potential in the galaxy is also oscillating. So if there is a light signal coming behind from that gravitational potential, the light will shift a little, the frequency will shift a little. From there, or by gravity. You want to ask, you can ask it. So I'll end here. I'll end by a very important thing. That in 1960s, physicists used to believe that cosmology is a speculative subject, because cosmology was mostly based on religious, mythological stories, and there was no objective proof. Today, it's one of the extremely precise sciences. We know the age of the universe up to very, very precise values. We know what rate universe is expanding. We know the geometry of the universe also up to very precise value. We know our universe is flat. Okay. And a lot of how structures are formed, how, why there are galaxies in the universe, and why universe is not completely homogeneous, why there is somewhere term. We know a lot of things. Okay. So the statement is not valid anymore. Obviously that was a wrong statement because he couldn't see. He is a great physicist. And this, I will end with this last sentence that you saw whatever I told you about this model is just simple harmonic oscillator, right? Only thing is there is a friction term and that friction term is changing with time. Only with that we could give a model of the universe. Okay. This original statement is by Sidney Coleman and I have changed a little bit. The red color is what I have added. If you are a cosmologist and you are working theory, then you deal with damn harmonic oscillators. Okay. Thank you. I extremely apologize that I didn't know the background is not ready. Otherwise I would have given a complete different talk, like the kind of talk I used to give generally. But I thought more because people are having astronomy club and all, some rotation club, dark matter history. That's okay.
This scalar field converts in case we need to consider the damping on very large and slowly goes slowly. Can it produce a inflationary scenario?
So I conclude. This is the unpublished work I was not showing to make this. This is phi dot and this is phi. Okay. What I have shown here, because there is a large damping term and inflation happened in early universe. So the rate of expansion was very high. So the damping was extremely high. So no matter how fast you push, very soon the scalar field will come to rest and roll slowly. So you get inflation. So wherever you start, these points are very high velocity and these points are low velocity or zero. Okay? Wherever you start, you meet these slow roll curves. These green curves are slow rolling curves. You meet those curves and get inflation. Only apart from if you start between these two arcs, this arc and that arc, the red color. So the possibility of, this is another generic nature of the universe. The possibility of not having inflation is very low. If there is a scalar field, most probably you will have inflation because see, most of the conditions will lead to inflation. Only in the small band will not lead to inflation.
So this is coming up in
this will come hopefully in 10 days.
This scalar field model, there is you must be aware of there is a limit is gravity where there is a control degree of gravity in scalar field and that can produce based on dark matter. How this model, how far and
in fact, sorry if you people don't answer, it's a bit different question, so I will answer it because it's a very important question also. You see, I told you this alpha attractive model, right? These are conformal supergravity models. They come from supergravity, conformally invariant Lagrangian. If your Lagrangian has two fields, phi and psi, and they are conformally invariant, then you can choose a case in which phi and psi can be converted to a new field. In that case, you get a conformal potential. And these potentials look like attractive potentials, like that. Okay. And putting these scalar fields can also come from very different places. They can come from string compacted fields. If you have extra dimensions in string theory, then you say that extra dimensions cannot be large. If they are large, I stretch my hand, I should go to extra dimension, and because my eye can only see 3 dimensions, I should not be able to see my hand. But wherever I move, my hand is not disappearing. Second thing is, if there are large extra dimensions, very large, then Coulomb's law will change. The fact that electric field of the charge goes as 1 by r square is only in 3 dimensions. It's a solution to Poisson equation in 3 dimensions. If you take 2 dimensions, it's log r. If it has extra dimension, it changes. You don't see them. So even if there are extra dimensions, they are very small. They are sort of curled up. They are curled on themselves. When you compactify them, those curled dimensions, from there also you get scalar fields. So scalar fields are natural predictions of all fundamental theories. In fact, string theory has those axioms that I was talking. String theory has some 24 axioms. They are there. What are they doing? Where are they? Now these axioms are used for dark matter as a model of dark matter, and this picture is called string axioms, like multiverse in inflation. It's It's called axioms. There are so many axioms. Each axiom has to put at a particular value to give dark matter. Those are extreme fine tuning, even more fine tuning. That point has not been realized once. Many great people work on axioms. That's a very hot field today in cosmology. So at that point is not realized. Just a minute. Have I answered your question?
Yes. I have another question. If you set the initial condition high at different points and different, and I may have a gradient.
Inhomogeneous universe.
Yeah. What kind of consequence?
A very good question. Actually, scalar field is a quantum field. The earlier it is in the universe, the more is the quantum fluctuations. So it is impossible that everywhere in the field the scalar field is at the same place. Right? Somewhere it's a little higher, somewhere lower. But as long as that quantum fluctuation is low, we are not going. Now because dark matter density is very low compared to inflation scale, so the quantum fluctuations are also very low.
You are working in classical regime of.
It's almost like classical. But inflation it will matter. And because it will matter, so at the end of inflation, somewhere inflation will over and somewhere it will not get over because it's little up and down. So somewhere matter will get produced and somewhere not. A little later. That's why the initial fluctuations were there, which grew over gravity and gave us. That's a beautiful story. Anybody wants to discuss about inflation, even if you are a first year, you should meet me tomorrow anytime. Okay, we'll discuss it from the beginning. It's a beautiful story. How all the structure is formed in the universe by quantum mechanics and gravity. And it's related to which question what is asked.
So another, in the context of multiverse theory, don't you think this spatial tuning of initial condition?
It's very important. It's very important.
Yeah. So it's all reasonable. It's
For
not like accidental.
Exactly.
It's probable. All universes.
All universes are exactly probable. In that sense, yes. In that sense, no. But the argument will still be valid here because these scalar fields are a very small value because their density is 2. For inflation, you don't care because there are so many universes that in some universe you have some value and some other universe you have other. But here, that's low. So it depends on how. So it depends on two things. First thing is, if the scalar field was there already when inflation was happening. If it is already there, then the question becomes very important. But if it was not there, it was produced after inflation, the inflaton field decayed to this kind of state, then what I am saying is still there. Okay.
So when it's oscillating, it's not very, mass scale is not grand scale.
It can be anything actually. Now first thing, it can be anything. The typical predictions from string theory are that these mass scales are very low. These are actually fields. The mass is given by the instantaneous density square, instantaneous temperature square divided by the symmetric square. Now because instantaneous square is not perturbed, it comes much later, so the mass is generally typically light. So they are naturally
It's
light.
not kind of reading when it's oscillating, not reading when it really
Because it's
slow.
natural. But if it is not from, if it is not an axiom or not from string theory, just a scalar field with m square pi square potential, then it can also give rise to inflation. In fact, it was a model of inflation. It still is. It's not completely ruled out. It's at the age, right at the age.
So the question is about like the weakly interacting massive particles we talk about. So apart from the particles that we know of, which you can think of as being candidates,
No, they are not.
if any other particle we are considering, then they might have also some kind of field kind of related to it. Then
The only difference is why I'm not calling them fields.
if those fields are also there, then how are these different?
Very good
And
question. Only difference
we have considered for the this also might should lead to some kind of particle.
It's a very, very important question. It's a question which I asked myself for many months before finally getting the answer. So I thought every particle has a field. Right? So those beams are also scalar particles. So they are also by scalar fields. So why this? I am calling this as a different model than those beams. The only difference is this field is at the vacuum when it's rolling. If it is the vacuum, there is no particles to think of. When it's rolling, so when it's rolling, it's in the vacuum. There are no particles. So it's like a vacuum energy of this interaction energy, which is V phi is acting. When it oscillates, it is a particle, but the mass is so low that the Bose-Einstein condensation temperature is pretty high. So these particles are there, but they are in form of Bose-Einstein condensation. So I can describe them using classical physics. Just like I can describe light by electromagnetic waves. Nothing, I am not saying nothing mystical. Just like I can use light by electromagnetic waves, I can describe while oscillation these are like particles. Before oscillation these are like vacuum. While oscillation these are like particles. When they are oscillating, the mass is so low that they are in Bose-Einstein condition. The whole particles are being like one fluid. So I am describing them by one fluid, which is fire. Fine?
So, so are we considering that the field, when did this field actually come to, like which standard for to say that?
Very good question. I don't know. So general class scalar fields. First year students, I am so sorry. General scalar fields come from spontaneous symmetry. So they have difference. Like this field come around 100 GeV. So this fields might have, the only question which is important in cosmology is whether they came before inflation or after inflation. So the model which I am using is supergravity model. So probably they came before inflation, but any other axiom like the standard model axiom, QCD axiom, that came much later. So for those you can think that those fields were produced when inflator decay. They were when universe is inflating, there is a lot of vacuum energy. That energy decay, and these particles. If there is a coupling, or they are always there, they were existing. If they were existing, then how did they survive the period of inflation? Because inflation throws everything out. My answer is because this field is in the vacuum. It's not oscillating when inflation is there, so there is no particles. The vacuum constant and it will stay there. These are no spectral fields. They will observation they will have signature.
So after the inflation, if you say this kind of these fields will exist, then they should have an imprint on the microwave background which you
They
can
do. So isocurvature perturbations. They do. But because these densities are low and this mass is low, so that isocurvature perturbation is low. But if there is a beautiful paper by Malda Sena and Nimar Kenyon, it's called Cosmological Collider Physics, in which inflation is used like a cosmological accelerator. But that they have studied for these scalar fields are there, but their mass is compared to the Hubble parameter during inflation. Very high, heavy mass, 10 to the power 16 GeV, and their signatures they have discovered. Signature of these ultralight particles have been discussed a lot. Their signature will be they can raise Hubble constant value. They can shift the phase of Barron acoustic. These are all hot fields. The terms that I am telling you were only published in last 2 years. Okay, they can shift. I am not an expert. Barron acoustic oscillation phase. They have it, but not on CMP perturbations. These are light, but other scalar fields can, which are heavy.
So you said that in the scalar field it is uniform throughout the, we assume homogeneity and it's uniform. So in a homogeneous universe we have dark matter in a homogeneous distribution. Like at every point the dark matter density is same.
Yes. Yes, but if that was the case, then how would it form the skeleton? If it's everywhere same, it's like a fluid, like water. What I said, that dark matter formed the skeletons everywhere, so that normal matter fell into them and formed
So
galaxies.
inhomogeneity is like necessary for.
Yes, inhomogeneity is necessary for any existence. Now, where did the initial inhomogeneity came? It came from inflation. When inflation ended, all the matter that were produced in the universe were almost uniform, but with little differences. They are almost uniform means if you see the CMB temperature, it's almost 2.7 Kelvin everywhere. The difference is from 2.7 Kelvin is, so the difference by 2.7 Kelvin, that quantity is 10 to the power minus 5. So like at one place it is 2.7, at other place is 2.7000001, at another place 2.699999. Only those small differences. So differences is temperature will be like differences in density. Hot means low density because they are moving faster. Okay. So those small density fluctuation was there. Now as time progressed, wherever high density was there, gravity tried to pull them. So over this 13.8 billion years, those things were being crushed and formed on the structure. So inflation is very important.
How do you get the form of the protein? The model was to find VV5, is it? So,
No, I didn't do that. That can be a process. What I did is there is already this V5 available in supergravity. Supergravity theory says that such a scalar field is there in the universe and it has this kind of creation. All I said is if its mass is low, then 10 to the power 82 orders of initial density from inflation will converge to today's length program. That's all.
So this V5 represents the interaction within
It's a quantum field theory.
within the scalar field.
It's a self-interaction.
Self-field.
Like from Higgs potential how it looks. It's a Mexican hand. So it's like a 5 to the power 4th minus 5 square. A 5 to the power 4th minus B 5 square. This is similarly that form which I have drawn up. The Starowinsky potential. So Starowinsky happened to be my guide style.
Maybe you said that there cannot be an observable surface of negative curvature. So why can we consider?
No, I didn't say that. I said we cannot think about it because what I am talking about is constant curvature surfaces. Constant two-dimensional curvature substances in 3 dimensions. Okay. What can they be? They can be a plane. A plane has zero curvature. It's a two-dimensional object in 3 dimensions. Okay. Or a surface of a sphere. It has constant curvature everywhere. It's a two-dimensional surface but in 3 dimensions. There cannot exist a constant negative curvature substance of 2 dimensions in 3 dimensions. There is not constant curvature. Constant. I am not saying just negative curvature. Everywhere it's same negative curvature.
So you have to say that you need higher dimensional Euclidean space.
Either you need, very good question. So either you need higher dimension. The minimum dimension which you need I think is 6 or 7. I forgot. I used to remember.
Say it's related to this embedding.
Yeah, I mean, we don't have to embed actually because anyway they don't know this. So differential don't anyway. So either you go to higher dimension or you deviate from Euclidean space. Don't stay in Euclidean space. Stay in this kind of space-time space, Lorentzian space, where distance between 2 points will be some negative sign somewhere. There you can embed. Then, in fact, if somebody wants to take a homework, just talk to me for 5 minutes and tell you how to derive that. This. If you have homogeneous and isotropic space-time, why would metric look like this? If you want to do this, go home and take a sphere and try to take 2 points on the sphere and try to find what is the distance relation between. You will see the distance will be like this. There won't be sin theta, those things won't be there, and the k will come as 1. It's very simple actually. If you want to do, then I can state the problem for you. Okay? It's a very interesting thing to do. Just no physics, just pure mathematics. Is that fine? I again apologize for juniors because the talk has to be for juniors to inspire them, not to make them bored.